When cyclic dienes are used in a Diels-Alder reaction, the same reaction that we've been learning takes place to give you a cyclohexene core in your product. But because of the cyclic diene, it takes a little more work to draw out the product. This is because when we use a cyclic diene, we get a bicyclic product in the Diels-Alder reaction. Let's look at an example where we use cyclopentadiene, and this is our cyclic diene. We're going to react this with a dienophile, and let's take a look at what happens. So let's start with just getting to our core structure, and for the core structure we're going to have the 4 carbons of the diene reacting with the 2 carbons of the dienophile to give us cyclohexene. There's our core product. But we have a little bit more to do here. So what you'll notice is that on these 2 carbons, we have our aldehydes, and we'll deal with stereochemistry in a minute, but let's just go ahead and draw the aldehydes in. And then on our diene, on these 2 carbons, connecting it, we have the CH2 group of the ring. We have to get that into our structure. So here are those 2 carbons, and effectively, we just need to draw that CH2 group in there. And there we have it. But we do need to deal with stereochemistry here. And as long as you're consistent, it's pretty easy to get the stereochemistry. What you always want to do is draw this bridging group, and this group that I've highlighted in red that bridges across the ring, that's our bridging group. Always draw it out using wedges. So let's do that. Here's our core. I'm going to draw the bridging group here with wedges. All right, now we have that. Now for our substituents, the aldehyde groups on the dienophile, we know that these are cis, so they should be on the same side. We have the option of drawing them out, or drawing them back. Now in the regular Diels-Alder reaction we had been doing with non-cyclic dienes, we would always draw both as 2 major products or the enantiomers of the reaction. In this case, you get these 2 products which are diastereomers, and it really depends on the orientation from which this group adds to the diene. The product where these 2 bonds are on the same side as the bridge with a wedge, that's called the exo product. The product where these groups are on the opposite side of this bridge is called the endo product. And it's found that the endo product is the major product of the reaction, not the exo product. So let's just define what the endo product is. That is when the dienophile pi substituent, or substituents in this case, the aldehydes, when they're opposite this small bridge that forms in the product. So if the bridge is out, these groups are back. That's endo. Let's take a look at this endo approach in 3D. So what I've done is I've taken our cyclic diene and just drawn it in this envelope style conformation where the bridge is pointed upwards, and here's the carbons of the diene, and here's the dienophile. And what that does is it approaches from underneath this bridge here. So here's the approach where we're going to get bond formation. And these two carbonyls end up going back, and the hydrogens will come up in the same direction as this bridge. So if we draw the bicyclic product in sort of a 3D fashion, here's how we'll do that. I'm going to start by just drawing almost what looks like a propane. A line up. Another line up. You're almost like you're going to draw a chair, but instead of going downward, which would give you the chair, what we do is we just draw a bond parallel to the bond on the bottom and then connect that over. And then we can draw our bridge pointed up. Here's our new double bond. Straight down for the endo, I have the aldehyde groups. And then for my hydrogen, here's one, and here's the other. So those would be essentially on wedges pointed up in the same direction as the bridge. So this bicyclic structure that I've drawn here is exactly the same as this structure. It's just two different ways to represent it. I'm not going to get into a lot of detail with this, but just to highlight the basics of why it's thought that this endo approach occurs. It's thought to be because of overlap between the p orbitals in the carbonyl and these p orbitals in the double bond. Versus if we were to flip this over to where the hydrogen were pointing in this direction, you wouldn't get that secondary overlap of the p orbitals. When your alkene dienophile is trans, the endo approach may or may not matter, and it depends what the groups are. So for example, in this first one, we have the trans alkene, but both of our groups have the carbonyl, so one's always going to be back and one's going to be out. If we draw our product, here's our six-membered ring. Here's our bridge. We're always going to have one of the ester groups pointing out and one pointing back. But now if we come down to our second example, here we have a trans dienophile, but now we have one substituent that is a carbonyl. And because of that, we want this group to have the endo approach. The methyl group doesn't have any p orbitals to worry about. So when we draw the product here, let's draw our six-membered ring. In this case, our bridge isn't just one carbon, but two. How do we show that? Let's draw a wedge, and then connect it by a bond. So from here, now we want to put the ketone back and the methyl out. And that effectively gives us an endo product because this functional group here with the p orbitals, the double bond, that is going to be endo to our bridge.